Hello and welcome to this video. In this video we are going to look at the required practicals, starting with the simple harmonic motion practical. Now this is the first of the A2 practicals. There are 6 of these, just as there were 6 of the AS practicals. We're going to go through one at a time to get an understanding of how to carry them out and why we're actually doing them in the first place. Now starting with simple harmonic motion, for all of the AS practicals, or most of the AS practicals, there wasn't really a specific measurement that we were trying to make. Instead, we're just trying to prove that an equation is correct. We have to test by experiment that these theories, all of this theoretical stuff that we've put together, actually make sense when we do it in the real world. And if you go back to remembering about simple harmonic motion, we came up with 2 equations. We had 2 different systems. We had the pendulum and we had the mass spring system. And we said that for each of these, the interesting thing about them was when we calculate their time period, when it's of a pendulum, it is only dependent on the length of the string and the gravitational field strength, and when it is a mass spring system, it is only dependent on the mass that is attached to it and the spring constant of the spring. Now, what we're going to do is put this to the test. If we now want to prove that this is actually the case and we have this kind of proportionality against T and L and T and M, we need to test this. We're first going to look at the case of the pendulum. Now, what we are going to say is we have 2 things that we could vary, which are the length and the gravitational field strength. Now, obviously, it's a lot easier for us to vary the length than it is to change the gravitational field strength of Earth, go to a different planet. So what we're going to say is we're going to try and prove that T is proportional to the square root of L, where L is the length of string. So our setup, first of all, is going to be a clamp stand. So we're going to have a clamp stand here like this that is going to hold a piece of string, and the piece of string is then going to be connected to a bob, and we're going to push it to one side and then allow it to swing and measure the time for these oscillations. Now, there are a few ways that you can actually investigate this relationship. The easiest way is to simply take multiple measurements for the time and multiple measurements for the length, so vary the length of the string, and this then leads us to be able to draw a graph, and that graph can tell us the relationship between these 2 variables. So what that means is we are trying to vary the length and then measure the time period. Okay, as we do this, we want to obviously ensure, as always, that our uncertainties are as small as possible so that we can fully make sure that we're getting the most accurate results possible. Now, in order to reduce uncertainties, the values of L need to be measured correctly. When we perform the theoretical derivation of all of this, this length L is actually if you remember from the video, I'll draw it up here, this was your starting line. We said that, let me draw this here, this was your equilibrium line, and we had a bob here. We said that we could make a right angle triangle here, where this is a right angle. Notice, if that is the right angle, this length L actually begins at the center of this circle, right? So when we actually measure the length of this string, L must be measured from the center of the circle. Now, if or center of the, let's call it a bob, so whatever's attached to this string. Now, if you don't do this, it's not a huge problem because you will still end up with the same proportionality. When you plot your graph, you're still going to end up with hopefully a straight line, and so you will be able to make the same conclusion The problem being is that you've now introduced a systematic error. Every single value is going to be shifted by the same amount, which is basically the radius of this sphere, which means that your y-intercept is not going to go through 0 as it should by this equation. That then means that you can't use those results to validate the entire equation, just this proportionality. If we were to make a simple correction, is just try and measure it from the center, we then are able to say that we could, from this experiment, then completely validate the full equation. So now we know we're going to have to vary L, and L is going to be measured from the center of the bob to the clamp stand. So this is the length L here. Then we are going to measure T. In order to reduce the uncertainty on the time, we don't actually want to just record one time period. We want to measure the time taken for a few oscillations. And I'm going to say between 10 to 15. Make sure you do the same amount of oscillations for each experiment to make sure that it's consistent. You don't want to do the time for 10 and then the time for 15, although you'll end up with the correct result, but your accuracy will be off. And so just make sure that you're keeping consistent with this. For 10 to 15 oscillations, and then you are taking the mean of this. Basically, you are then just going to divide by the number of oscillations to get the time period for a single oscillation. So this then leads to you being able to measure T. Now, in order to say that this is true, you can repeat each of these things. We said in the simple harmonic motion video that one of the things that this is independent of is the starting position. For the same length, you could do, so just to prove this a little bit further, for the same length, you could, if you have time, take measurements of T for 3 different starting positions. Now, if you take it for 3 different starting positions and find that it doesn't matter where you begin, you end up with the same time period, you've now proven that, as the equation predicts, this is independent of your starting position. Now, that's not entirely necessary in order to get the pass that you need in this, but it is something that can then maybe give you more to write about in your conclusion or your analysis section of your write-up. So now we have results. We obviously need to take these results in a table. We're going to have basically the time period in seconds, and we're going to have the length of the wire, or the length of the string, which we're going to measure in meters. And we're trying to prove this proportionality, so we actually want to plot a graph of root of L, which is meters to the half. All of these have to have the uncertainties, so make sure you're adding your errors in this whole thing. So make sure your errors are present. And then your graph is going to be a graph of T against root L. So T here against root L here, and you should find that you will get a straight line. Therefore, you will end up with proving the result that T is proportional to root L. And this is the main point of this experiment. Now, I said by measuring L in this way, you can actually prove the full equation, because that means if we have used this from the equation, it means that 2 pi over root g is actually the gradient. So therefore, I can take the gradient of this, and the gradient should equal 2 pi over root g, which is a constant because the gravitational acceleration of Earth is constant. So you should find that it doesn't matter what group in your practical or your class do this, the gradient of everything should always be the same. Okay, and it doesn't matter their starting position, it doesn't matter about any of that. Their gradients should always be the same because you're all on the same planet. Okay. Now this is how we do a pendulum. If we then wanted to observe how we would do it for a mass spring system, we're following a very similar kind of logic. What we are saying for the mass spring system, if we recall the equation, we are trying to prove a relationship either with the mass or with the spring constant. Now, again, we have to decide which of these is going to be easier to do. We can either keep the mass the same and then have a bunch of different springs, or with a different known spring constant, and then we could investigate the proportionalities between the time period and the spring constant, but that's going to take a long time, especially to have a series of known spring constants. It's much easier just to put on a different value of the standard mass. So what we are going to investigate or attempt to prove is that T should be proportional to the square root of the mass that we attach to this spring. Now our setup is going to again be a clamp stand, and this clamp stand is going to have a spring attached to it, and that spring is going to have some mass m attached to it. Again, it doesn't really matter where your starting point is, whether you start at equilibrium or whether you have a big amplitude to start off your oscillations, whether your amplitude is small. As long as you've started it off and you have the same mass and the same spring, so the spring should stay the same, you should be able to then make these measurements. Now the mass is very easy to measure, so we need to measure, or even if we keep consistent, we are varying the mass and we measure the time. To vary the mass, we're just going to have the addition of multiple different standard masses, right? So we can have, you usually get these kind of systems like this where you can add on as many standard masses as you like. So you will vary the masses using standard masses. Now the thing about standard masses that are good is they carry very little uncertainty. So for A levels, as long as we're concerned, we actually don't really care about the uncertainties of that because they're not going to make a huge difference. Therefore, we just have to make sure that we are measuring the time period or the time for 10 to 15 oscillations, and then dividing by the amount to give the time period for a single oscillation. And once we then have the time period for a single oscillation, we add on more mass. We do the same thing again. Once again, you can do this. So you could, for the same mass, start from 3 different positions, and this would again allow you to prove that it is independent on your starting position. And then from that point we can say that we can have a table which includes the time periods that you measure in seconds. It has the mass in kilograms, and it should have the square root of the mass in kilograms to the half. And all of these things have to, as always, carry some errors. Now the mass and the square root of the mass actually probably won't need errors in this case because they're often deemed as being negligible unless you're given them by whoever is supervising your experiment, but your time should definitely have some uncertainty on it. From this, we're then going to do a similar graph as before. We are going to plot the time against the square root of m. We should get a straight line here, thus proving that t is proportional to root m, where the gradient in this case should actually be equal to 2 pi over root of k. Now this should be a This is because you've got a straight line. This is obviously constant for you because you have the same spring, and your spring constant isn't going to change by just oscillating. However, you can't now compare this with other groups in your lab session because they are using different springs, which means their spring constants are going to be slightly different, and therefore you're going to end up with some variation. Whereas in the pendulum, you're all on the same planet for definite, so you will definitely have the same values for that. So this is then how we can verify both of these equations. So using a fairly straightforward experiment for both of these, we can now verify that our theory is correct in lab, and this is how we do that. Thank you for watching.